And yeah. Okay, good. So let me start by a happy birthday. And thanks a lot for all the great job, great work that you've been doing, guys. Um, so it's an honor to be part of this celebration. Um, I want to tell you today about a work which I'm pretty excited about. It's called Quantum Algorithmic Measurements, and it's joint work with Jordan Cotler and Qi. And it's not yet on the archive. It's going to be on the archive hopefully in the next few days. And it's kind of a culmination of a few long line of works and thinking of me and others about the question of how to think about quantum measurements in a general way. So I'll be mentioning also many other works along the way of myself and of others. Okay, so you see here there is a. Oh, by the way, do stop me, ask questions. It helps me understand where the audience is, especially now that I can only see something like 5 people of the audience. So I really appreciate that. Okay, so from Wikipedia, a measurement is the testing or manipulation of a physical system in order to yield a numerical result. So we'd like to investigate this statement a little bit. Okay, so why doesn't it move? Okay, so so this work starts from basically the observation that we have been witnessing in the past, I don't know how many years, not just a single revolution, but several revolutions in quantum computation. So the first one is the discovery of quantum algorithms and cryptography and the exponential speedups. And in this revolution, the connection with physics was basically just the question to physicists: can you actually realize quantum computers? And what is the right model? About a decade after that, I would say a new revolution in quantum computation emerged, and this is the revolution of quantum Hamiltonian complexity, in which physicists actually started to realize through the work of computer scientists and through the combined work that there's a lot to be learned about quantum systems from the computational perspective. So actually the interaction between physics and computer science became, I think, much stronger, much more conceptual. The third revolution, which is the one which I think is least recognized, and it's the one that I would like to talk about today, is the revolution of quantum algorithmic measurements, which is, by which I mean the penetration of computational ideas into our very understanding of how to perform quantum measurements. And I mean quantum experiments or measurements in the most general sense. Okay, and what we've been witnessing over the past 10 years is that the process of quantum measurements has started to include more and more computational aspects to it. Both in the way we think about quantum measurements and also in the way we actually implement quantum measurements. And I want to give some examples. So let's start from a very simple, well-known example of a quantum experiment that does not include these computational aspects to it. That's an X-ray diffraction experiment where we have a crystal sample and we want to somehow determine its atomic and molecular structure. And we shoot some X-ray photons at it, and it scatters, and the photons scatter off it. And there's a camera that detects the angle and the position and the intensity, etc., of the photons, and deduces from that something about the structure of the crystal. So there's not much quantum computation going on here. But then let's look a little bit further into more like later quantum measurements. Where we have added computation ingredients. So quantum computation ingredients. So one such example is, I think, an interesting example. That's the example where we have, it's an example from metrology. We have some frequency that we want to estimate with very high precision. And the problem is that when we want to estimate a frequency, well, we need the signal to be there for a long time before it decoheres so that we have enough precision. So the usual, and what we have here is 1 over square root of t, that's the standard quantum limit, that's the usual precision. Using some sort of very primitive quantum error correcting codes, not encoding the actual physical system, but just sort of adding another qubit or two to the system, which are very reliable and which sort of serve as some place to perform error correction with very primitive manipulations. One can actually enhance the precision and arrive at the Heisenberg limit. And this was actually also tested experimentally. Okay, so this is a very interesting, this is the experimental test, and I recommend reading this paper for a more theoretical analysis of this and understanding of how, when, and how this can be done. And this is sort of a picture of how this works, where this is the probe, and there is a superoperator acting here, and this is the additional qubits that are added for error correction. It's not, again, it's not a full error correction. The state itself is not encoded, but this is somehow serves as additional degrees of freedom, and there is some kind of a quantum error correction going on here. Okay, so that's one measurement process, which prolongs the time the signal is still meaningful to increase precision. Okay, another example is a Gedanken example. It's a kind of a mind-blowing, highly non-realistic example, but still, it's a very fun experiment to think about. That's a famous Hayden-Preskel black holes as mirrors experiment, in which this is a black hole, and one needs a quantum computer to collect all the Hawking radiation emitted from this black hole. And once this can be done, then the hypothesis that black holes radiate quantum information quickly can be tested. That's related to the information paradox, and there's been a lot of recent work on the information paradox recently, which is sort of related to extensions of these ideas. And you can see here that this kind of experiment requires basically quantum memory close to the quantum black hole, which is the physical system. Okay, so that's another type of experiment. Another one, which seems again very different, is an experiment designed by my student Yossi Atia and myself, in which we observed that Shor's algorithm can be viewed as an experiment for estimating the energy of certain eigenstates, of all eigenstates of a certain Hamiltonian, to within exponential precision, in a way which is efficient. So this is an exponential violation of the time, energy, uncertainty principle, and this requires a quantum computer to essentially simulate the evolution with respect to this Hamiltonian. This is a Gedanken experiment, but it shows that with a quantum computer, you can sometimes do things which are very surprising, like exponential violations of the time, energy, and uncertainty principle. And the fourth example I want to mention is that of quantum interactive experiments. So again, this is sort of something that comes from a different world. We have a quantum computer. We want to verify whether it's running correctly, whether it's performing as it should perform. And there's been a long line of works on this problem. And basically, what we know is that if a verifier has a few qubits, it can interact with a quantum system, and if this interaction is performed in a structured way, then the verifier can get convinced that the quantum system actually performs the correct evolution or the desired evolution, even though the verifier cannot simulate that quantum system because it only has O of 1 qubits, and we assume that it's too hard to simulate. So we arrive at something that we will call interactive experiments. And this is, again, some kind of a computational aspect that we introduce into experiments. This was tested with very small examples, also experimentally, for blind quantum computation, which is sort of a sister protocol to that. The picture here shows that in one version, it actually, in order to do this, this uses random quantum error correcting codes, but this is not necessary. The bottom line is that this uses interaction between the system and the experimentalist in a way which is structured and which requires some kind of quantum computation. Okay, so with all those examples in mind, we can ask, what is a physical experiment? Like if this is really, I've shown you just a few examples, but I'm sure any one of you can come up with tons of more examples of things that happened recently, and it kind of it's not clear what is the most general model of a quantum experiment. Okay, so as you see, there is a variety of points of view on this in this slide. So okay, so what we want here is basically an answer to this question that we will want to model a quantum experiment in a universal way, in the most general way. And moreover, we want to model it so that we're able to actually answer questions like, what is the computational complexity of a given experimental task? And what is the resources required? What are the resources required to perform such a task? Okay, so what we are looking for is a computational complexity model of measurements. I'm using, again, measurements in a very hand-wavy way. I don't mean actually apply a measurement and get an outcome. I mean the full process of manipulating the system and at the end getting some outcome. So it's a synonym for experiment. Okay, so this is the main question. And my plan for the talk is basically to tell you about two things that we did along these lines, attempting to answer this question. So first of all, we actually have a proposition for a model of a general quantum measurement process that fits the era of quantum computers, that fits this idea that we can actually incorporate elements of quantum computation into the experimental system and interactions and so on. We call it QUALMS for quantum algorithmic measurements. Okay, and I'll most of the talk I'll devote.
There's a question.
Sure.
Someone is still stuck between in the equivalence of Shor's algorithm and energy levels of Hamiltonian. So the request is if you can go over that again and how it violates the time energy uncertainty.
Oh, I'd be happy to actually answer this in the question and answers part of the talk, because it kind of diverges us. I gave this sequence of experiments just to give an idea of how diverse experiments can be. And if that particular example wasn't clear, then there were other examples. For now, the only thing I wanted people to take out of it is that is to get some sense that computational elements could very much help in quantum experiments, and they have been incorporated in the past decade in those in various experiments. And what we're trying to do is to give a theoretical framework to that, what I view as a revolution, so that we can actually study it. Okay, study it theoretically. So, okay, and please get, if I don't remember the person who asked this, please ask me again at the questions and answers part. Okay, so I want to introduce QUALMS. QUALMS is this quantum algorithmic measurements, and using this this model of QUALMS, which will take me some time to introduce, this will enable us to apply some rigorous study to the capabilities and limitations of quantum measurements. And so this will lead us to various questions, which I'll tell you about. And at the end, it will lead us to a theorem, which is our main result of the work with Jordan and Xiaoyang, that there's an exponential advantage to coherent QUALMS over incoherent QUALMS. Essentially, coherent and incoherent, in a very, for now, think of this as with a quantum computer and without a quantum computer. But we'll get to a much more detailed version of this later. Okay, so let's start. QUALMS. Okay, so how do we actually start out thinking about what is the right model for a general, what is the most general computational model for a measurement? So we go back to this useful example of X-ray diffraction, and I'd like to extract from it a few observations. So the first thing is that, just like it was said in Wikipedia, experiment is something that computes a function. So the function is a function from the physical system, all possible physical systems, or under some assumptions possibly, to a classical output, some numerical output of the measurement. Now, another thing that we can notice in this experiment is that our access to the system is not complete. We don't actually have full access to this input, to the physical system. We definitely don't have a classical full description of the system. And we also don't have a quantum full access to the system, meaning there's many degrees of freedom which are hidden from us in the sense that we don't have access to them. Our interaction with those physical, with the crystal here, which is this physical system, is only through these photons that scatter off it, and the camera interacts with those photons. So we have quantum interactions with just a limited number of these degrees of freedom. Okay, so these are some observations, and let's start by, first of all, thinking of what will be the Hilbert spaces that correspond to the description of a general quantum experiment. Well, we have this, our workspace. We have a register of degrees of freedom which are not accessible to us, and we have something that interacts between them, and we'll call these three registers nature. This is something that sort of nature keeps to itself. This is everything that describes the system and everything that nature needs in order to remember what the physics is, but this is inaccessible to us. There's another register, which is the laboratory. That's what is accessible to us out of this physical system. And there is the third register, which is the workspace. And in this case, in the X-ray diffraction experiment, the crystal, the actual crystal is nature, is assigned this N register. The photons are the laboratory, the lab register, and the workspace is this camera and computer and whatever we have in our lab. Okay, so these are our Hilbert spaces, but now we want to somehow say how the QUALM is built using these Hilbert spaces. So I'll give a cartoon, and then in the next slide I'll actually define it. So the cartoon is some kind of a hybrid between quantum interactive protocols and black box algorithms. It's a very simple model, but it's just important to put all the necessary ingredients in. So these are the ingredients. First of all, the quantum experiment will just be essentially a quantum algorithm. So it will be just like a black box algorithm. If you cover the register N, this is time. If you cover the register N, it will just look like a quantum circuit interacting with some black box acting in between. Do you see my mouse when I'm moving it? Yeah, okay. Maybe I'll use this, it's easier. Okay, so however, here we have also this hidden register N, which enables the quantum system both to remember its state and sort of its physics, and also it allows some hidden degrees of freedom which the quantum circuit does not have control over. So there is interaction between the register W and N through this register L, because the quantum circuit acts only on registers W and L and not on N. It's inaccessible. So that is a part of the interactive protocols. And it's black box because we don't have access to these super operators corresponding to the physical system, and neither to this state. Actually, this state is not part of the black box. Usually the black box is just the super operator, but we extend it with this state. So there are a few more ingredients before I move on. to the actual definition. So first of all, what's the input? So the input to the system is this physical system. So I'll describe it later. We'll call it lab oracle. But it's both the input state and the super operator describing the physical system. So we only describe the physical system by two things, the input state and the super operator. And there is the output of the experiment. This is sort of the thing that the thing that we actually compute, the output of the function. That's a classical output. And then we also allow classical input. Beyond the quantum input, we also allow classical input that sort of provides some parameters. For example, if the problem is to estimate some observable of a Hamiltonian, I don't know, the Gibbs distribution at some particular temperature. So the classical input could actually give us the temperature. Okay. So these are the ingredients, and now I want to go to actually say the definitions in a more orderly way. Okay, so here's this picture again, and there are three main players. The first player is this lab oracle. It's just a pair of two things. One is the input quantum state to the register n, and a superator acting on the two registers n and l. And this lab oracle is not known to us. This is what describes the physics. Now, the second player in this QUALM theory is the task. The task is sort of what we set up to do when we start to design an experiment. This is what we want to measure. So what we want to measure is sort of a function of the input of the physics. So the task is using, under the restrictions of, well, we only have that set of gates, G, given some restricted set of possible lab oracles, meaning we assume that our lab oracle, our physical system, is taken out of some set of physical systems, and some classical parameters, output some output. In general, that could be a probability distribution. This is what I wrote here, but more simply, it's just a classical output. That's a task. And then what is a QUALM? A QUALM is simply an implementation of this task. So it's a quantum circuit made of these gates, G, interlaced with oracle calls to this lab oracle. And very naturally, what the QUALM will output is it will initiate the system with row of n on the register n, tensor some basic state on L, tensor some input state on W, will run the quantum circuit with calls to the oracle, to the actual lab oracle, and then we'll output some output. And we will say that it computes the, if it actually outputs this F for all lab oracles in the input set, we will say that it performs the task, it achieves the task. So that this is our model. Maybe it's a good place to actually, well, maybe I'll go through the examples, and then maybe it's a good place to take some questions. So back to examples. Here is again, I didn't change anything. It's just the definitions.
There's a question. But to make oracle calls, we do not know what rho n and epsilon nl are already, right?
Right. So the idea is that this model actually models what happens in the lab, meaning this thing models what I imagine will happen in the lab when we can implement this super operator. And we can also implement some quantum gates on the side. So it's not that we don't need a description of this super operator. We actually can apply it because we have the physical system that we're trying to measure. Okay, so this is like we have a Hamiltonian which we're trying to estimate some parameter of that Hamiltonian. So we can plug in some initial state, and we can let this Hamiltonian evolve for some time. And this is the lab. This is the superoperator that corresponds to the lab oracle. We don't know this Hamiltonian yet, but we can still apply it. Okay, if hopefully this answered the question, but good. So let me give some examples of how this works. So I've already talked about the fact that this is an obvious generalization of black box algorithms. When n is empty, we just have a superoperator, usually a unitary, and you just apply the quantum circuit. But this is not the same quantum circuit, of course. This is different circuits, and in between you can apply the black box. Okay, so with the X-ray diffraction example, N is going to be the crystal, L is going to be the photons, W is the camera, and between W and L, there's actually no quantum circuit. What we are allowed in the X-ray diffraction is not quantum gates, but this is just some very simple classical interaction, basically, that detects the location of the photons. So we can think of this as from abstractly as a classical interaction that that sort of registers where the photons are and what angle they hit the camera, etc. Okay, let's look also at the measurement using a quantum error correcting code. Here, if you notice, basically, if you remember, we had a probe, we had a physical system. And we added to it, well, that was the physical system, and we added to it some, say, 2 qubits to make it, to prolong its coherence time. So these 2 additional qubits will sit in this working space, and there will be a quantum circuit or some quantum operations that somehow use these 2 qubits and make the signal that sits in this lab register more coherent, or lose its coherence less. It's a nice exercise for those of you who were familiar with verification protocols to actually try and put the model of the problem of verification inside the QUALM model. But I won't do it now. Okay, so let's see what we have here. So this is a good time for questions on the model, because we'll move on now to the computational complexity aspects of this. So wait, should I wait or?
I don't think there are questions.
Okay, good. Okay, so if all is clear, we want to understand the computational complexity of different QUALMs. Meaning we have a model, now we can ask thousands of questions. What is the computational complexity?
The question did come in. I guess it took some time to type it. The question is, in the measurement using quantum error correction example, are there any lab qubits or L qubits?
Yes, there are L qubits. These are the qubits that we actually have, that we actually measure. Everything that we have access to is part of the lab register. Nature register has only degrees of freedom which we don't have access to.
We also have the work register. We also have access to the work register, right?
Yeah, the work register is sort of completely controlled. Yeah. The lab register is something that we share with nature in the sense that we can implement some things on it, but there's also nature that implements its own superoperator on it. Okay. By the way, just sort of brainstorming, we can actually think of a Hamiltonian model instead of a quantum circuit model in which these things happen in parallel as Hamiltonians rather than sequentially, but that's not what we did here. Okay, so okay, obviously we have set up the ground so that we can actually ask the question, what is the QUALM complexity of a given task? This would be counted, well, naturally as some function of the number of oracle calls or queries and the number of gates. And for there's no real meaning to actually combining the two because these are apples and oranges, but it does tell us something about both quantities, which you want to minimize both of them. So we'll call this the QUALM complexity, and if you want, you can weight them differently if in the system some of them, one of them is more expensive than another. Okay, so this is our QUALM complexity, and the point is that now we have a way to ask about the computational complexity of measurements, and it becomes independent of the exact physical implementation, just like in quantum circuits when we talk about complexity of functions. It's basically independent of the platform that we're using to implement a quantum computer, or at least we will be using to implement it. Okay, so we want to study QUALMs from this computational complexity viewpoint, and there are many questions we can ask. Okay, with this model. I mean, you have a model, you can ask infinitely many questions about it. For any given task, you can ask what's its computational complexity, what's its QUALM complexity. So how do we even start? Well, we decided to start with the question that interested us most, which remember, this motivated the whole research from the beginning, which is this issue of incorporating computational ingredients in quantum measurements. We would like to understand how much do these computational ingredients help us? And in order to understand how much they help us, we need to somehow restrict, we want to somehow compare the full QUALM model, which has no restrictions. It can use a general quantum circuit. It's assuming that we have access to a full-blown quantum circuit. We want to compare it to some model which is restricted, and where the vast majority of quantum experiments nowadays sit. Okay, so we define this model, which we call the incoherent QUALMs. So what are incoherent QUALMs? Basically, incoherent QUALMs require that there will be incoherence between applications of the superoperator of the lab oracle, both in space and in time. So that's very hand-wavy. More concretely, first of all, what I mean by incoherence in space is that the interaction between the work register and the lab register will be by a local LOCC, local operators classical communications. So there's no quantum interaction between W and the rest of the system, or between W and the physical system. The communication is just classical. This could be quantum. This is obviously quantum. There could be very complicated operations on L, but the interaction is classical. That's incoherence in space. Incoherence in time is that we require that between every two applications of the superoperator, we apply a complete measurement. Okay? And so this basically cuts off the coherence between the state of the lab oracle at time t and the time t+1. Now, notice that this is still a very general model in the sense that, first of all, it's adaptive. You can, for example, prepare a very complicated state of n qubits and feed it to the super operator here, and then measure it in any complicated basis at the end, as long as you perform a complete measurement at the end. And these measurements and preparation of basis and basis of measurements are adaptive, could depend on previous results. Okay, so this is our incoherent QUALM model. Okay, and now I can state, I think, the results. And the results are that that there's a provable exponential advantage for coherent axis over incoherent axis, even adaptive. So basically, we have found a very simple quantum, actually two quantum tasks, which we call fixed unitary problem and detecting symmetry problem. I'll describe them in a moment. And we show, first of all, that in the coherent version, when we have a full quantum computer, they're easy to solve. Their QUALM complexity is linear in the number of qubits. But and this is very easy. The algorithm is going to be very easy. It's just basically some variance of the swap test. The difficult thing is to show the lower bound. and the lower bound actually is not so difficult in the non-adaptive case. What's really difficult is to adapt it to the adaptive case. Okay, so I hope I'm not overselling this, but I think that this is a new type of exponential advantage for quantum computers. This is, so I'm happy to discuss this in the discussion part, but it seems to me like this can be viewed as a different exponential advantage. So after I present it, maybe this can be actually discussed.
So
There are a
a
few
couple of
questions.
Oh, sorry. Would you like to postpone them till later, or shall we try and deal with them now?
Maybe I'll define the problems and then we'll deal with I'll answer them.
Okay.
Okay,
Yep.
so the problems are this. The first task, the fixed unitary problem, is the following task. It's a distinction between two lab oracles tasks. So basically we're in the lab, we have either one of two physical systems at our hands, but we don't know which one. And the two physical systems described by two lab oracles are those. One of them has picked a unitary according to the Haar random measure and remembers it forever. And this is the unitary that it applies every time the oracle is called. It applies this unitary on the L register. The second lab oracle picks a new unitary every time it applies. So it applies a newly random Haar random unitary that it picks every time the oracle is called. And we're looking for a QUALM which distinguishes between the two. So the description in terms of a lab oracle, the input state and the superoperator is basically done by the nature state is going to be a mixture over all classical descriptions of the unitaries, of all possible unitaries. We don't care about the size of nature and how it presents it. And we don't care about accuracy. So we have this state, and so that's your initial state, and then conditioned on this description, apply this unitary to the L register. This problem is physically motivated. I would say weakly, but still there is some motivation. It's a toy model of this, of distinguishing between time-dependent versus time-independent Hamiltonians or systems. Xiaoliang told me that it's related to a question in Floquet systems, but I don't know enough about it to say. Okay, the other problem is a very much related problem. It's the symmetry distinction problem. In this problem, we have access to 3 lab oracles. In each one of these 3 lab oracles, the lab oracle picks a random unitary and remembers it forever. But now the random unitary is picked out of 3 different ensembles. One is the unitary group, the other is the orthogonal group, and the third is the symplectic group. And I won't go into the definition of the symplectic group, but I'll just say that this again is motivated physically by the fact that these 3 ensembles correspond to 3 different types of time reversal symmetries. So, okay, so these are the 2 tasks, and I'll hint about how these how the proofs go, but let me take the questions first.
Okay, shall I relay them, or would you guys like to ask them yourselves?
I can go ahead and ask. Maybe that's fine. It looks like I'm first up. Yeah, this is Don. So, hey, Dorit. Very nice so far. Thank you. A very simplistic question about the model itself. When you were saying something about the lab having to do complete measurements, and as a cryptographer, when I hear a declaration, I immediately want to break it. So my question is fundamentally, is how necessary is that assumption? Is it a requirement, and can you circumvent it in a sense by having epsilons which sort of stuff superpositions or entanglement back into nature and use nature itself as in a cheating way to avoid some of those complete measurements?
Well, I have 2 remarks to say. First of all, it's an excellent question in the sense that I don't know the answer. In the sense that we actually our dream result would have been without this requirement of complete measurements, and just allowing entanglement between, just either allowing or disallowing entanglement between W and L. That is sort of a much, it would have been stronger because we put less restrictions on the QUALM. However, I want to say that these restrictions on the QUALM, it's not something that, at least in what I'm viewing, there's no cryptography questions involved, because this is motivated by physics, and the physicists actually say, okay, this is all we can do. So it's not that somebody's trying to sneak in more power, it's that somebody doesn't have enough power to do the full thing.
Gotcha. Makes a lot more sense that way. Thanks.
Okay.
There was more questions.
Sure.
Christian?
Yeah, so I was wondering whether quantum query complexity is somehow fits into this model, right? Because it seems like if you use the the oracle provided in quantum query complexity as the nature system, or this the quantum channel that nature applies, then this should kind of fit into this framework, right?
Do you mean quantum query complexity in the sense of quantum black box models?
Yeah, exactly.
Yeah, so as I said, I think this is, where did they put it? Sorry, where is this example? Here, black box algorithms are a special case because when n is empty, this is, you just reduce to the black box algorithm model.
Ah, right. Okay. And then it's clear that you get a similar separation because of, like for a quantum query algorithm, if there's a complete measurement in between each oracle call, then you don't get the usual exponential advantage like in Shor's algorithm, right?
Yeah. Okay. Great question. No, that's wrong. So I actually thought that nobody would ask the question, so I put it only at the end. But thanks for asking the question.
You can totally postpone the answer to the end if that helps.
No, let me answer this more. Okay, why don't we postpone the answer to your question? The answer is, I would like to argue that no, Shor's algorithm and Simon's algorithm all live in the incoherent model. Okay, that's my claim.
Okay.
And so, in fact, Shor's algorithm, in fact, Simon's algorithm does not provide an exponential speedup, an exponential advantage in between coherent and incoherent, because it just lies in the incoherent model. In fact, it lies in a very, very incoherent model where everything is in a product state, because Simon's algorithm just applies Hadamard basis measurements and preparation in the Hadamard basis of the initial state. So that's a short answer, but if that wasn't understood, I'll get back to this later.
Thanks.
Thanks for this question. This is important. This is very important. This is basically the whole point. It's a subtle point, but it's the whole point is that this is a different question. It's not a question of what is the power of quantum black box algorithms. It's a question of what is the power if you have a black box to incoherent interaction between that black box and something else. It's really physics motivated. What will you do with a quantum computer interacting with an unknown physical system in order to measure that? So Simon's algorithm just doesn't need this extra qubit or extra qubits to interact with. It gets the full exponential advantage without any coherence or any entanglement to another system. Okay, so I'd like to give, maybe I'll finish the talk and then we'll get again to some questions and answers because I have just a few more slides, just to give you some idea of the proof. So first of all, as I said, the upper bound, as is usual, unfortunately, as usual, things are very simple because we don't really understand enough about quantum algorithms. And one of the biggest questions is whether actually we can design more interesting QUALMs using this framework. But for now, our problems, the problems that we found is actually something that, I mean, we have QUALMs which are very simple, but incoherently, it's impossible to achieve them without exponentially many queries. They're not only simple, the QUALMs in the coherent model, but they only require a linear number of gates. So it's not in query complexity, but it's in QUALM complexity. So the upper bound is simple, the lower bound is difficult. Okay, just to give you a snapshot of what the upper bound looks like, it's a swap test between maximally entangled states after some conditional unitaries or conditional matrices were applied, since this is in the symmetric, in the distinguishing between the symmetry problem. So we don't know if it's unitary or symplectic, etc. So I wrote it here as a conditional A. So you don't need to understand it, of course, but it's just a simple concatenation of a few swap test ideas. Okay, it's the difficult part that's interesting, the lower bound. And the lower bound, as I said, the interesting thing is here in the lower bound for the adaptive case. It goes by, first of all, don't expect to understand it. It's, I don't know, 20 pages proof, but I just want to give you some kind of a flavor of what are the players that go into this. So the first thing that goes into this is reducing incoherent QUALMs to a slightly simpler version of incoherent QUALMs, which we call simple measurement QUALMs. I've removed here the N register because it just has conditional U. And here we are talking about, remember the problem is whether U is fixed or chosen uniformly at random every time the oracle is called. So here U is fixed. And in a simple measurement QUALM, we only have complete measurements in some basis, which can be dependent on previous measurement results. That's simple measurement QUALM. Now, the reduction to this case, if you're familiar with probabilistic algorithms, it might seem to you like, so what have we removed from here? We've removed the intermediate other POVMs and the conditioning on their results. And it could look artificially as something that is very similar to a probabilistic algorithmic argument in which you replace a probabilistic protocol, for example, by a mixture over deterministic protocols with the weight corresponding to the right, to the value of the random variables. However, here the random variables may depend on previous results. So that usual argument doesn't work. We need to work much harder, but it still works. So this is the easy part, a reduction to this simple measurement QUALM model. Within the simple measurement QUALM model, what we have is we need to somehow calculate the probability distribution over all measurement results. And if you look closely into this, this turns out to be, this is the probability distribution over all measurement results. S is sort of all measurement results for K oracle calls. And if you look closely into this, into the actual probability distribution, what we get is some kind of integrals of this form where AS and BS are the choices of the basis that could, as I said, depend on the previous measurement results. Now, if you're familiar with such integrals, you would notice that what goes into this is very similar to integrals of the form of products of unitary elements and their complex conjugates, 2K of those. And there is a very, very elaborate theory to actually compute such integrals called the Weingarten functions, which actually translates such integrals into a sum over elements from the permutation group on K elements, where K is the number of query calls, where W is this Weingarten function. And what goes into this is a representation theory of the symmetric group. And what we needed to do with all these Weingarten function machinery is that we needed to look at the permutations. And the thing is that these permutations somehow talk about the permutations between, it's a different time orders of the answers of these oracle calls. And the permutations need to be such that we can actually perform the integration even though there are dependencies. And so we need to look at different partitions of the permutations which actually allow such dependencies not to occur. So that we get into these fun I don't know, diagrams of permutations like that. And I just wanted you to see those diagrams, and I bet you understood nothing from this slide, but just so that you glance at it. Okay, so that's it for the proof. That's all I can say for the proof. As Dawn asked, this complete measurement requirement is kind of annoying. We would have liked to actually separate just between fully coherent QUALMs and QUALMs which disallow coherence in space and allow coherence in time. In fact, some experiments actually do that nowadays. Coherence in time is sort of less counterintuitive. So we would like to know that the lower bound actually holds even when we remove this complete measurement assumption, but we don't know that. And it's a curious question. I would like to know if this is true, or maybe without complete measurements, we don't need this coherence between L and W. Okay, and just to summarize, to wrap up, our motivation is physics, and what we have tried to do here is to provide a general theory for algorithmic measurements and their computational complexity. We think, after checking many examples, that it looks like the theory does cover a universal model for measurements. And we've derived an exponential advantage for coherent QUALMs over incoherent QUALMs. There are many open questions. I'll mention a few. I've already mentioned and explained this, the fact that this exponential advantage is different than Simon's advantage, because Simon's advantage does not need this coherence. It actually lies in what we call a local model. There's no W register. It's just the preparation and measurement are all in a tensor product basis. So we think of this as a new exponential advantage for quantum computers for applications for experiments. And there are many open questions. Perhaps the most interesting one is the exponential, whether we can actually arrive at exponential advantages like that in the NISQ era. Because the moment we introduce errors and noise, everything breaks down. The swap tests don't work anymore, and we don't have fault tolerance. We don't even have fault tolerance, even if we do have fault tolerance, because we are talking about physics. I mean, the physical systems themselves don't have fault tolerance. So, so the question is this realizable, or is this relevant in realistic settings? And then there are obvious other questions, but maybe I'll wait for, I'm happier to listen to people's questions.